Thanks, Fabrizio, for the invitation introduction, and congratulations on your new position. I'm going to talk about the policy learning with asymmetric utilities, and this is the joint work with Ila and Koske. I will be focusing on the treatment policies in this talk. And the treatment policies are the decision rules that assign the treatments to individuals based on their characteristics, such as age, gender, medical histories, and so on. And there are many examples of treatment policies. The algorithmic recommendations use data and the model to predict the best treatment option for each individual. And the personalized medicine takes into account each person's medical history or genetic information to determine the most effective treatment. And to make informed treatment decisions, we often need to combine the statistical decision theory with causal inference. The decision theory helps to characterize the treatment decision using the decision function, and the utility can measure the value or benefit of the treatment, allowing us to weigh the risks or benefits of different options. And in many problems, the outcome can be influenced by the decision. So it's important to take into account how the decision affects the outcome. And this is why causal inference plays an important role. And there is a fast-growing literature on policy learning. The classic setup in the literature considers either randomized experiments or unconfounded observation studies. So we have the covariates xi for each individual, and a binary decision DI, for example, 1 for the use of a new drug, and a binary outcome Y, such as the survival indicator. And the potential outcomes Y1 and Y0 represent the outcome that would have happened if we had chosen the decision 1 and 0. The treatment policy, denoted by pi here, is a function that maps the covariate space to the decision space. So given the value of the covariate, the policy tells us which treatment should be assigned to the individual. And we focus on the deterministic policies in this talk. So pi is a deterministic function of x. And for the deterministic policies, if units have the same value of x, they will always receive the same treatment decision. And to measure the value of the treatment options, we need to specify the individual utility. And the most commonly used utility is a function of the decision made and the observed outcome under that decision. So for example, if the policy assigns a patient to take the treatment, then pi of x equals to 1. And if the patient survives under that treatment, then the potential outcome y of 1 also equals 1. And then we will have the benefit of saving the person minus the cost of the drug. And the final utility is b minus c. And different values of b and c will lead to different utility functions. And our goal is to find a policy with a high expected utility. So it's the expectation of the individual utility. And the idea of the concept of this expected utility is based on the idea of maximizing the greatest good for the greatest number. So by finding a policy with the highest expected utility, we can make sure that we're making the decision that benefits the most people possible. But since we focus on the expectation, it's still possible that for some of the units, the decision leads to an undesirable outcome. This classic utility function works well in many problems, but may lead to controversy in some high-stakes settings. And here is the trolley car problem, a famous scenario in ethics and psychology. A runaway trolley is on its way to collide with 5 people, and the driver can divert the vehicle to kill just 1 person on a different track. And if you were the driver, what's the right thing to do? So from the perspective of maximizing the expected utility, it seems that killing 1 person is better than killing 5. But this raises ethical concerns because it involves actively choosing to kill someone. And similar issues arise in the scenario of autonomous car driving. And in this case, the people on the two tracks are changed to people in the car and the pedestrians at the crossing. And depending on the decision of the driver, the car may hit the obstacle and kill the people in the car, or hit the pedestrians at the crossing. So these two examples show that the classic policy learning framework may not be appropriate in some high-stake applications. And let's take a closer look at the utility function in the classic setup. Suppose the treatment is binary and the outcome, the treatment is binary, taking a new drug, and the outcome is the survival indicator. So with this binary decision and a binary outcome, we can classify the individuals into 4 different subgroups based on the joint potential outcomes Y1 and Y0. And these joint potential outcomes characterize how the decision would impact the outcome. So if Y1 and Y0 both equal 1, the patient would survive regardless of the treatment. And we say the treatment is harmless to the patient. And if Y1 equals 1 and Y0 equals 0, the patient will survive only if taking the treatment. So the treatment is useful for the patient. And if Y1 equals 0 and Y0 equals 1, the patient survives only if not taking the treatment. The treatment is harmful. And in the last setting, the treatment is useless. And for each of these 4 subgroups, we can compute the utility change between taking the treatment versus not taking the treatment. And this characterizes the usefulness of the treatment in these subgroups. So for the harmless group, if taking the treatment, the patient will survive. So we will have the benefit B minus the cost of the treatment, B minus C. And if not taking the treatment, the patient will still survive. So the utility is B. And the difference between these two utilities is minus C. And for the other 3 groups, we can compute the utility changes similarly. And if we ignore the common cost term in these utility changes and focus on the benefit terms, we can see this positive B here comes from the utility gain of assigning a useful treatment. And the minus B here comes from the utility loss of assigning a harmful treatment. And by using the classic utility function, we will always have the sum of these two to be 0. And this is the symmetry restriction in the classic utility. It assumes that being useful is equivalent to avoiding harm. And more generally, this restriction holds as long as the utility function depends only on the treatment decision and the outcome under that decision. But in many settings, we may not think that being useful is the same as avoiding harm. In the trolley car problem, we may think that actively choosing to kill someone is much worse than diverting the vehicle to save 5 people. So to relax this restriction, we consider generalizing the utility function to depend on the joint potential outcomes Y1 and Y0. So this utility depends not only on the observed outcome that under the decision made, but also on the counterfactual outcome that would happen if under a different treatment decision. And we call this asymmetric utility. It's asymmetric because the utility gain of assigning a useful treatment, denoted by UG here, can be different from the utility loss of assigning a harmful treatment, UL here. And then the classic utility becomes a special case when UG is the same as UL. And we can choose different values of UG and UL to reflect different real-world scenarios. In the trolley car problem, we can assign a utility loss of killing someone much greater than the utility gain of saving the 5 people. So with this new utility, our goal remains the same, to find a policy with a high expected utility. And but this new utility leads to additional difficulties because the utility involves the joint potential outcomes. So we propose a new framework for learning the optimal policy under this new utility function. And we focus on randomized experiments or unconfounded observational studies in which these two standard assumptions hold. And the unconfoundedness assumption assumes the decision is independent of the potential outcomes given the observed covariates. And the overlap assumption assumes the decision in the data is stochastic. So each unit has non-zero probability to receive the treatment and control. And to illustrate the basic idea, let's consider the symmetric case. So in this case, the expected utility can be written as the expectation of the decision function pi x times the effect x. And this effect x is the conditional average treatment effect. And it's identifiable under the confoundedness assumption. And from this expression, we can see to maximize this v pi, we only need to assign pi x to be 1 if effect x is non-negative, and assign pi x to be 0 with negative effect x function. And this leads to the optimal policy in the symmetric case, denoted by pi sim here. It assigns the treatment condition to the subgroups with non-negative conditional average treatment effects. And numerous methods have been proposed for learning this optimal policy from the observed data. We can directly estimate the conditional average treatment effect, and the estimated pi sim is then the indicator of whether the estimated effect is non-negative. But this approach relies on the correct modeling of the outcome. And another branch of methods write the problem as the empirical average of this decision function times the difference between two scores, gamma 1 and gamma 0, computed for each individual. And the construction of these scores shares a similar idea of the methods for estimating the average treatment effect. So there are different choices of these scores. For example, the inverse probability weighting score depends on the propensity score, and the doubly robust score depends on the propensity score and the outcome mean. And after estimating these scores, we can solve this standard optimization problem to obtain the estimated pi sim. And this is the symmetric case, but with the asymmetric utility, the expected utility has an additional term, harm x. And this is the probability of y1 equals 0 and y0 equals 1 given x. And it's the proportion of the harmful group. And let's first assume we know the value of this term. So similar to the symmetric case, the optimal policy will assign the treatment condition if the term within these brackets is non-negative. So if UG is larger than UL, which means that being useful is more important than avoiding harm, then this right-hand side is negative. And the optimal policy will assign the treatment decision more often than the symmetric case. And if UG is smaller than UL, which means that being useful is not as important as avoiding harm, the right-hand side becomes positive, and the optimal policy will assign the control condition more often. But this harm x function is not identifiable because it involves the joint potential outcomes. So even if we can write the optimal policy as a function of harm x, we cannot estimate it from the observed data. And the issue here is that with the new utility function, the expected utility is not identifiable. And to deal with this issue, we use the robust optimization approach. And this approach focuses on the regret of pi relative to a pre-specified alternative policy phi. And this regret is the utility difference between the alternative policy and the target policy pi. And it measures how much utility we lose if we use pi rather than phi. And if the expected utility is identifiable, then maximizing v pi is equivalent to minimizing this regret because the expected utility of a given policy is constant. But when the expected utility is not identifiable, the robust optimization approach will give different results for different alternative policies. So we need to first specify the alternative policies to compare with. And we have three choices. Two practical alternatives are the never treat policy and the always treat policy. So the never treat policy assigns the control condition for all the units, and the always treat policy assigns the treatment condition for all the units. And another one is the oracle policy, which is the optimal policy if we know the unidentifiable term harm X. And after specifying these alternative policies, the robust optimization approach considers the maximum regret over all the possible values of the unidentifiable term. The idea is that since we don't know the value of harm X, we consider the worst case. And the worst case has the maximum regret over all the possible values of harm X. And then the optimal policy is the one that minimizes this worst case regret. And we call this the minimax policy because it's the solution to a minimax problem. And to find the minimax policy, we need to first obtain all the possible values of harm X. And this is the same as deriving the partial identification bounds for harm X, and it's well studied in causal inference literature. And using these bounds, we can obtain a general form for the minimax policy under different alternative policies phi. And the nested optimization here is simplified into a single optimization in the form of a weighted classification problem. So the pi x, the target function here, can be viewed as a classification function, and the terms within these brackets are the weights. And the C1 and C0 correspond to the scores for each individual, and the C is the cost function. And these functions depend on the symmetric policy pi sin and the nuisance classifier delta plus, and the function forms vary with different alternative policies. And as a special case, if UG is the same as UL, we will have C1 equals 1, C0 equals -1, and the cost function equals C for any alternative policy. So the robust optimization approach reduces to the classic policy learning. And to solve the minimax policy from the observed data, we can replace the terms in the general form with their empirical analogs. We can first compute the scores, IPW or the W robust scores, and then estimate the pi sim and delta plus from these scores, and then obtain the weight and cost functions, and finally solve this weighted classification problem to obtain the minimax policy empirically. And in our application, we solve this classification problem using the SVM. And I'll skip the theory since I don't have enough time. And we applied the method to classic.
Yeah, sorry, I think in a couple of minutes, in principle, the next session should start.
Okay,
it was also my fault. So if you can, yeah.
I'll go through this quickly. So it's a classic observational study on the RC, the right heart catheterization, with about 5,700 ICU patients, and there are 66 covariates, and the decision is inserting a catheter into the pulmonary artery, so it's an invasive and risky procedure, and the outcome is the survival indicator by 30 days. We first estimate the W robust scores, and from the scores we compute the average treatment effect, which is consistent with previous studies. And then we use the data to compute the optimal policy under different settings of the UL and UG. So we fix UG to be 1 and vary UL from 0.5 to 2. And and we consider the decision rules that use the RC if the estimated probability of surviving 2 months is below a threshold. And this estimated probability is a covariate in the data. And this vertical lines shows the different thresholds when we vary the value of UL. And you can see as UL decreases, the threshold increases, making the optimal policy to treat more people. And we also consider the decision with all the 66 covariates. And so some concluding remarks. Many decision problems involve asymmetry between being useful and avoiding harm. And to characterize such asymmetry, we need to consider the joint potential outcomes. But this leads to the non-identification of the expected utility. So we focus on the minimax regret policy, but this generates additional difficulty the minimax policy depends on the choice of alternative policy, and we need to specify many different parameters in the new utility function. And there are many possible extensions, and I'll stop here, and thanks for the listening.
Thanks a lot. Faster and more effective than myself. So I guess if there is one question for the speaker, otherwise I have just a curiosity. So first of all, I guess the paper is on archive or not?
Yeah,
is available on archive. And mine as well. So I didn't mention, but you can find the details and everything on the latest archive version that we uploaded a couple of months ago. And also the harmful proportion that you can bound is essentially the proportion of the principal strata conditional on the axis, right?
Yeah.
So again, essentially, you can also include monotonicity or not, or maybe use
with
kind
monotonicity, it's identifiable. So it just directly solve the optimization problem. You don't need to
all right. But of course, you are then saying that the effect goes only in one direction, which of course is yeah, okay. But just to understand what underlies the problem.